Here we go, friends. Turn on that thinking brain.
Wait, let's do like that deep breath thing.
You need a deep breath moment? Need a rectangle breath? Okay, rectangle breath. Ready? Let's do 3, 6. So in 3, out 6. Ready? In 3. 1, 2, 3. Pause. Out. 1, 2, 3, 4, 5, 6. Pause. In. 1, 2, 3. Pause. And out. 1, 2, 3, 4, 5, 6. I can just like feel relaxed when you guys do that. Okay, so titrations. Okay, objective of today is kind of similar to the buffer date, but we want to understand titrations from all 3 sides of our triangle. Okay, we're going to do one right in front of you, so you'll see it with your eyes. Okay, we're going to draw pictures of what it looks like at the molecular level. That's what we're going to do on our brain boards. And then we'll talk about the symbolic mathematical side of it as well. Okay, it's what you went over last time with that activity, and now we're just hopefully piecing it all together. Okay, now with a titration, what it is, when you hear that word, first off, do not put it in a box of only acids and bases. Okay, it can be applied to other things in chemistry. We're just using it in talking about acids and bases. What a titration is it's a lab technique. You have to have the equipment. We'll talk about what the equipment is. Okay, but it's a lab technique to determine one of 2 things about a substance. Okay, primarily it's used to determine an unknown concentration or actually maybe a completely unknown substance where I have no idea what this thing is. I'm going to compare it to something I do know, and that will then help me figure it out. Okay, so with this idea of it, let's talk about our equipment here. So we have, whenever you do a titration, you use this device called a burette. What the point of this is to deliver a liquid in very slow drop by drop amounts. Okay, that's the point of a burette, is it just makes it very, very controlled. That's why it's so long, but there's various sizes of them. Okay, the burette always holds your known substance. So if you want to label that on your picture, you have a picture of one of these things, and put in this flask, in the burette, is where I put my known substance. So for our titration we're going to do today is we're going to titrate sodium hydroxide, which I know its concentration. It's a 0.1 molar solution. I'm going to fill it up a little bit more. You have to use chairs when you do titrations if you're not tall enough. Alright, okay. Now the way the burette is set up is it's actually numbered backwards. So 50 is down here, 1 is at the top. Because what we care about is the amount of liquid that's coming out. How much have I dispensed? So I didn't fill it all the way to the top, but it doesn't really matter because I'm just going to compare where I start to where I end to see how much has come out. Okay? So I'm going to put a starting, I'm going to make a little list over here. Last period we started at 4.6. We're at like 6.2 is our starting volume. I'm just going to keep track over here. Okay, and it's a 0.1 molar solution. Underneath your burette in your, what's called your Erlenmeyer flask, is where you put the unknown. So we want to label that on your picture. So this is where we put our unknown substance. Now you do want to keep track of the volume that you use, because that's going to be important, even though I have no idea what its concentration is. So this is a concentration of hydrochloric acid, and I have no idea what molarity it is. So this is our unknown substance.
Is that a lie or is that a...
You have no idea what it is. No, I'm not lying.
Like 1 molar?
I happen to know what it is. But
Dang it.
Yeah, see? That's what I thought. Ah, I win.
But you can know what it
What was the other thing that you lied about?
I think you should
melt
a
Yeah, just like mixing salt water. See, actually, yeah, this is the same thing.
Just water all over again.
Yo, are you gonna drink this?
Now, with this, okay, you should have learned last time about the equivalence point in a titration. Show me with your hand, by drawing in the air, where's the equivalence point on a graph?
What?
I'm sorry, how do you want us to show that? See, you can figure it out. Good, so the equivalence point is the middle of your vertical asymptote. You're familiar with that word in math? Okay, the very middle of it is the equivalence point. Now let's correct maybe something in case you got this misunderstanding from our activity. The equivalence point does not have to be at 7. pH of 7 is not the definition of equivalence point. So change that in case you made that link last time. It can be 7.
Is it around 7 or is it just a complete range?
It can be anything. Yeah.
It's not always
Yes. So what is the definition? This is what I'm going to circle. The definition of the equivalence point, the equal part of it, is the moles. Circle that word moles. Okay? The equivalence point is the point at which the moles of this equal the moles of that. Because if I know this, then I can find that once I get to that equal position.
So during a titration, you're trying to get to the equivalence.
Yes, that's the whole objective. Yes. Now, the way to do a titration experimentally is you would then put in here a pH probe. So this is a pH meter. Okay, I'm not going to put it in for today's sake just because we're going to do the visual side of it, but when you do it,
We're gonna do this?
yes, you guys will do a titration yourselves in the lab.
No way.
Okay, so this would go in here, and this measure, and then this links up to my computer. So as it's running, we would get that beautiful graph, hopefully. Okay, now you can also do a visual side to titration. It's not as accurate, but visually you can kind of see that change that's happening. So what I'm going to do, because visually, so you can see this, I'm going to add universal indicator to my acid to see as that pH is changing.
Doesn't that change the concentration?
No, it doesn't. Because you're only adding, I guess, yes, in micro scale, but because I only add a few drops, not really. And in the end, it doesn't change the amount of moles that are there, which is the significant portion, right? So that's why I measure the volume before. So the volume was 25 to start out with of my unknown. So it doesn't really change
25
the.
milliliters?
Mm-hmm.
That doesn't seem like there's a lot. Well, that seems like a lot for that visual kind of stuff.
Elsa?
Yeah, wait, is the thing, like, is the whole, what's it called? The sodium hydroxide, the burette?
Yes.
That's 6 milliliters?
No. So it's at the starting mark of 6.
Oh, okay.
So technically, there's 44 milliliters in there right now.
That's
does that make sense?
That seems like a lot more than 6.
Okay, I'm going to add a stirring magnet. So this will stir automatically for us as we
I
drop.
love those things.
Okay, just add a little bit more for the people in the back. Okay, all right, so let's find a good speed here. Okay, so now we're ready to start our titration. So the objective is we want to add this until what point?
It changes
The number of moles are the same. Now in terms of the indicator I put in, and because it's a strong, so if the moles of strong acid and the moles of strong base are the same, I make water, and so when it turns to green, right? This is the way to actually, if you wanted to, I don't know why you go through the work, but this would be the most exact, precise way to make the salt water and drink it safely. Because you're literally adding it to drop by drop, versus just, let's pour 2 beakers together,
So
right?
could you do this?
Well, now that I put indicator in, I definitely would not want to.
What?
It's just gonna indicate your insides. It's like.
But yes, this would be
Because
like,
I want
It looks like. It looks like.
if someone said you have to drink your experiment, this is the experiment I do.
We could take out.
Not yet, so not until I start adding.
Why would it just like drink baking soda? I would drink that.
That's gross.
Salt water.
Couldn't you get the indicator back out doing the one thing where like you boil and like depending.
Oh yeah, like there are separate.
Yeah, so you could get your salt water and then boil the salt and the indicator out and
And
then
then
have
just
water.
make really nice water. That'd be like, I made this water myself.
I made this water
It's
myself.
supposed to have
Homemade.
acid, but no longer.
You like open your fridge, there's a bunch of bottles of water, you got homemade water. So, this
Yeah,
is
that
just
one's
a
gonna
random
kill you.
question. What is the stir made out of?
It's just a magnet.
Because you just,
Oh,
is it like,
it just has, yeah, some sort of plastic coating
you
that.
just like toss it in acid, like do you have to replace that thing?
No,
Cool.
yeah, it's whatever plastic it is, it's
Pretty good.
So you can just throw it in anything.
as far, I put it in everything and it's never gone away on me, so.
That's
Sweet.
some high grade plastic.
I've never put it in like
The strongest acid.
the strongest acid I have.
Wait, what's the strongest?
How many
acid?
magnets, sir, is
I have an 18 molar solution.
Oh!
That's
Wait, what
gonna
about
burn your
hydrofluoric
eyes
acid?
out.
Or like pure fluoride, what's
I
that
don't
non-sweet
have
plastic?
any hydrofluoric acid yet.
Oh.
That's hard to store safely.
You have multiple of them.
Special
Wow.
cabinets for that stuff, right? So I should show you guys though sometime too that, so I have a special cabinet just for acids. And I should show you just, cause metals are very reactive with acids. But, and they're all like in things, right? But like the stuff around the cabinet, like you can, it's starting to like corrode from just the fumes.
That's so cool.
Dude.
Like the
Show us
lock, like it's not like broken, but like the lock, like you can see, like doesn't look quite normal anymore. So.
That's awesome.
Okay, so here's what we're gonna do, and I'm gonna walk through with this one, and then on the one on the back, we're gonna do a second titration. You'll do that then on your brain board, and you can earn up to how many? Do they? I think you could earn up to 20 smiley faces today.
Oh,
Okay.
The whole percent.
yeah, them all.
Now, with that being said, don't let me forget, if you're wanting to turn them in for this term, we need to turn them in at the end of today. So, and I won't put them in until after corrections are done.
Or could we like put them in next term?
If you want them for this term, oh, I won't, so what you can do is you can turn them in, and then if after corrections you're at an A, I won't put any in. Does that make sense?
No, she'll just use all your smiley faces.
You'll get 130%. So yeah, so pretty much like, a lot of you will turn it in last period as like, I might need these, but that's the last thing I put in.
It's like a 5.6. You're like, what?
I'm not here tomorrow, so when I use them, I'm gonna at least tell them.
Either concentration of H, right?
Yes.
I think a lot of so why is it that like when you change the concentration of H, the indicator doesn't change? Because like as you're adding it, it's like it doesn't change the concentration.
So let's,
Right, there's this one from the lab thing
yeah,
where they all are different concentrations, but they're all the same pH.
that's the
Yeah, it's different concentrations, but they all start with pH.
Well, yeah,
Oh, because if they're stronger, yeah, and how to create, that's what I see. Okay, so here's our three pictures, ready? Alright, give me your attention, so it's time to get to the smiles at the end. Okay, so in this box, we're gonna draw a molecular viewpoint, okay? I'm purposely, if you have a two different colors of things or something, I'm going to purposely use two colors to indicate acid versus base and to show how things are created. And then in this box, so this is the molecular view, this is your eye view, and then down here is where we'll talk about the mathematical symbolic side of it. Okay, so first one is before I start the titration, I haven't dropped any base yet. Okay, before the titration, if I could magic school bus in there, what would we see floating around?
Bunch of H3s and other stuff.
Good. It is HCl. I'm just going to use HA just so it stays generic, right? So does a strong acid exist as HA or HA? Okay, so write that in here. So
No,
it's
you're
magic
fine.
school bus.
It's magic.
What is it made of?
I don't
Magic.
know.
Magic.
Okay.
A darn good
Draw
plastic.
only 3
It's darn good plastic.
because ratios are extremely important here in understanding, and if you draw more than 3, it won't follow my pattern as we go. But. Okay, so it doesn't matter a whole bunch, but why is the pH so low at the beginning?
Because we don't have any bases.
Because it's a strong acid, and you have a lot of H+, right? Because the pH is literally a measure of how much H+ is floating around. right? That never changes. This is the definition of pH. And we only have strong acid, and so obviously that's the only thing influencing the pH. Okay? All right, now we're gonna start our titration. So when you do a titration, we are adding the base to the acid. It could be reversed, depending on what the unknown is. With the goal of, what am I trying to get to?
Neutrals of 7.
In this case, 7, but what's
it's not always that.
the main goal?
To get to the equivalent.
Moles are equal, right?
How
So-
would you be able to tell that if it wasn't 7?
That's where you'd use a pH probe to get, because the equivalence point will always show you. So, yeah, great question, because otherwise you're like, I don't know what it's gonna be, right? Okay, now when you do these, they can be quite stressful in a lab setting, because as you'll see as we go, you want it to be a controlled flow, but not too fast, but also I don't have all day. Because when we zoom to molecular view, how many molecules are in a drop?
So
A lot, right? And so one drop to the next drop can be too many when it comes to a titration. So you have to be prepared to stop it at a drop, right? Some people really like these, some people it's way too stressful. Now, I know where the equivalence point is, so I'm going a little faster than what you would even maybe do in a lab setting. Because if you have no idea when it's coming, you want to keep it controlled so that you can get that nice, clean change. Grant?
So in this, is there a typo? Because it says, like the third word down, I'm not sure if that one's a typo. It says stopcock, and I'm not sure if that is a different word.
So that's what this thing is called.
Okay.
So when it's vertical, that opens it. When it's horizontal, it closes it. Okay, so we don't want to get to our equivalence point yet, so I'm going to stop it there. So we added a decent amount of base. Okay.
Everyone get a moment to giggle.
Okay. So
It was gonna happen, like, we were all thinking it.
okay, when I start adding my NaOH,
Oh, that was funny.
okay, so we started dropping the base. What's changing at the molecular view? What is the base doing to the solution?
The OH is bonding.
We're bonding.
So OH bonds with H plus making, say again? Water. So I'm going to draw a water molecule, but notice I'm going to circle it in red to indicate it was created from those two things coming together.
How
Okay.
many?
Oh, it's like the
Just one.
Just one.
Yeah, I'm just going to draw one. Okay? Okay, then,
Then we just keep adding on.
so these ones haven't reacted yet, so keep in those guys.
Isn't there an extra A minus in there? Or like an A?
So what else am I missing?
We're missing our next A.
Oh, but then also it's
So it's gonna be NA.
Oh, yeah. So we also have the spectator that came with the OH.
Isn't there 3 A minuses?
Oh, thank you. Good catch, Milo. So yes, so one of the A minuses is still there because
Yeah.
there's right. The H got bonded with, but the A minus did not.
Yeah.
Interesting. Okay.
Gold star.
Questions so far? Okay, coming down here, where's my pH at before the equivalence point?
1.
Still low, right? So it's definitely
Low.
still less than 7. It's still an acidic solution because you still have H pluses floating around, and H pluses make things acidic, right? Which we can see from the graph, right? That it goes up slightly, but every drop of base that is added, right, just gets neutralized. So, yeah.
Why is it so like hard to be like once you've gotten to like the middle? Why does it go up so fast?
Great question, Joel. Love that question. Should we get to the equivalence point and answer it as we go? Okay, so everyone good here before? Let me see if there's anything else I want to do today. Oh, let's write this equation. So the equation that's happening here is H plus with OH making O1. Okay, so write down that's kind of the equation for this step. Okay, the difference is we still have excess H plus so it still stays acidic.
This
Yeah.
is one of these really stupid questions that involves drinking things.
Oh, great.
Could you do like a titration but with your stomach acid by like drinking a base?
Oh.
Yeah. Titrate your stomach.
I mean, yes, you could.
What the-
Do I recommend it? Okay.
You're also fascinated with it, I know.
Okay, I'm gonna go a little faster because I kind of know when it's gonna get close. That way we don't have to watch the water.
Yeah. Personally, I just.
I mean, it's not water.
I guess I'm just gonna not take
The trust issues.
I'm just saying, like, if you were really trying to be accurate.
Never gonna trick my class to get.
If you wanted to.
Not how we go.
No, bro, it's
Just
like.
look on your faces when I drink.
Like, I
So it's like an automatic, so like you can just like.
No, they just keep it on.
Is it really hard to get over saying someone doing
Yeah.
We'll just go for the
Okay, so, leading off that question, what Joel asked is if you notice from the graph that it changes very drastically, right? Like it's here and then vertical asymptote straight up.
Straight up.
So do you see it starting to change? Okay, so we're not there yet.
Oh, it's yellowy.
So notice, so we've reached probably like this curvature,
Oh, we're about to shoot.
right? So we're getting close.
So, do you stop it, like, right when it turns green? Is that the equivalence point, or do you need to let it wait a second when it's green?
We want it to stay green. So you'll see that sometimes it will go green but then stir back.
Okay.
So we want it to stay green. Now there
It's
is
like
a
long
difference.
Straight line.
This is visual. So we don't call, when we go based off the color, we actually call it the end point, not the equivalence point.
Okay.
Because it visually it could be off. But that's where the graph is the most accurate way. But so
And your pH thing that you would have stuck in there shows you the graph on there.
yes.
Okay.
Yeah. Okay. Now notice we're gonna hopefully not go too far. So notice you can see that it changes, but then it goes back.
Ooh, that's so cool.
But that means it's getting close
Dude, that's magical.
to what it wants to be, and that's where you don't want to freak out and then turn it the wrong way.
You're literally making
Is there-
potions of death.
Oh.
It's
It's
yellow.
closer though.
It's back.
It is really mesmerizing.
Are we there?
So it's like lingered.
It's like.
It's getting pretty funny. This drop. Come on.
It's so weird to watch change color.
It's so magical.
I did 2 drops. Was it too many? This is where these are, they're fun in the lab, but they can be
Stressful.
a stressful thing.
Did we get it?
That was so close.
But it's not as
It
yellow.
kind of
It's
looks
getting
greenish,
closer.
right? It kind of looks greenish.
Can we get your keys to the ice?
To go get some ice. Yeah, do you know where to go?
I hurt my leg and I need ice. Yes.
Oh, that's probably what I should call. You know where the room is. Bottom of the stairs, like, that will get you don't lose my keys. Do you guys know them?
I do.
Can someone vouch for them?
Yeah. They'll,
Don't lose my keys back.
I don't know what they're using the ice
They're just
for,
like
but
some
you'll get the
scams. Like,
keys
let's go
back.
get
I
the
don't
source.
know. The ice
This
is.
is changing back. Are we seeing how fast like the reaction of H to like OH plus O?
No.
Yeah.
That's pretty close to neutral green though. I think green.
I think it's
One more drop. One more drop.
But then it's always stressful because then you might do 2 drops. Or sometimes you get too excited and then you just do a whole waterfall and then.
But I like it when it's blue.
You like the blue color.
It's there. I'm calling it. I feel like we need one more.
Okay, we're gonna do one more and then we're just moving on.
Wait. Yeah,
But if
one
it
more.
needs another.
Yeah, it's
It's green, it's green.
It is green.
Wait, be careful.
Yellow green.
Oh, 2 drops.
No!
Did I go too far?
Wait. Oh, it's
No.
turning.
Oh.
It's going back.
Yes.
That's it.
That's actually
it right
that's a
there.
good one.
Perfect.
Yeah, that actually is really green.
You got
Yeah.
great
Equivalence point.
kids.
Ish, right?
Now it's officially base.
Okay, so now, safe for drinking. Okay, so what do we have?
We have an equal amount of moles between.
Good, so write that at the bottom first. So
Yeah.
the key definition is that the moles of H plus, actually let's not put H plus, let's just put acid. Okay, the moles of the acid equal the moles of the base.
Wouldn't it eventually react all the way even if it was a weak acid?
So this is always true at the equivalence point, yes. So even with weak ones, the moles of the acid still equal the moles of the base, meaning all of it is fine.
But since like it all reacts at the same like since it doesn't really matter like a rate, since all of it is like all of the if it was a weak acid, all of the weak acid is like well not all of it, but some of it's like solid. Well not solid, but like
Together?
it's all some
So
of
you're
it's
saying-
together. When the base gets rid of some of the stuff that's like making it apart, wouldn't that make it so that more of the together stuff like comes apart until like eventually all of it reacts?
Yeah, you can like in a sense force that equilibrium, right? Equilibriums don't naturally go to completion, but if you keep pulling something out, it will force it to.
Would that mean that eventually it would always turn to 7 if the moles were equivalent?
No, and we'll talk about why though. But everything you have said up to that point is true. So the first thing to recognize here is that the number of waters created matches what?
Number of H.
Right, the number of H's that I started with, right? Okay, so what else should I have in here still?
A minus and.
How many A minuses?
3.
Because those aren't changing, right? They're just hanging out. And what else?
And A.
And how many of those? Good. So there's quite a few times on AP Chemistry questions, they love to do this on multiple choice, and you'll see this on your homework tonight, is give you these particulate views, and you want to pay close attention to what's there, but then also how much is there is the other thing. 'Cause sometimes you can narrow down to like A and B, and they both have the same substances in there, but then you got to pay attention to the ratios, because that's important too.
So would weak acids have like a higher equivalence point, like a higher pH?
Yes. So when it's a weak acid with a strong base, the pH is always bigger than 7. Yeah. Okay, questions with our picture here? Okay, let's do the math. I'm gonna do mine over here, just because I have a little bit more space. You should hopefully have room just to do it below that box. Okay, so we now want to determine what is the concentration of our acid. Okay, so we stopped our titration now at 32.1. Okay, if I'm at my equivalence point, what do I know?
There's equal amount of moles of both acid and the base.
Yeah, the moles of acid equal the moles of base. So if I find the moles of base, that equals the moles of acid. And then to get to concentration, we would just divide by the volume.
Oh.
So the first step is, well, let's find out how many moles of base we used. So, difference between these two numbers, how much did I add?
So many.
Is that
I
right?
can get that.
Yeah, 25.
Okay, so we added 25.9 milliliters of base. We know its concentration is 0.1. Now, without doing any math, if I raise a hand, does anyone have just a prediction about what is the concentration of our unknown acid?
0.1.
Why, Grant?
Because they're the same milliliters.
Look, we added pretty much the same volume. So if the volumes are the same, what does that mean about the concentrations?
They're the
They're
same.
probably the same. So if this was multiple choice, don't do the math. Just look at it, because most of the multiple choice problems are like, it's equal to this, or it's greater than this, or it's less than this. right? And you don't need to go through the math process, just think about it logically. So, hypothetically speaking, don't say anything out loud. You're gonna put your answer on your boogie board with your neighbor, okay? We'll do the math here in a second, but this is just a hypothetical. So hypothetically speaking, if I added, let's say I had to add 50 milliliters of base instead. Let's say that we had to go all the way to the bottom. Does that mean the concentration of the acid is greater than or less than 0.1? So if I had to add 50 base, does that make the concentration of the acid greater than or less than the concentration of the base? So put greater than or less than. Yep. So if I added, so hypothetically, if I had to add 50 instead of 25, what does that tell me about the concentration of my acid? Is it greater than or less than?
It's less than because they're the
Yeah, 0.1.
like if she's saying two actions. But I'm saying like you're saying that if you had to add more of this, what was it saying?
50 mils of base, yep.
Like if that were to say that, it would be less.
All right, in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Show me your brain. Boom.
This is funny. I didn't have time to.
We wrote it in a variety of ways, but I think we're mostly there.
If your concentration was higher of that, then you need more of the base.
So if you said greater than, you can have a smiley face.
Wait, are we right?
What I meant.
So like, if you needed more.
Right, so think about it for those that had it backwards.
Yeah, you're right.
If I needed more base,
More moles of acid.
then there's more moles, so we had to balance it out, right? No, you didn't have to just. Okay, now let's do the actual math, because if it was FRQ, right, and we need an exact answer.
Let's get it there.
Okay, so first step is I need to find the moles of base. Step 1, moles of base. So, what's capital M?
Molarity, so moles
Which is?
over liters.
Good. So 0.1 equals X over liters.
Yeah.
Everyone good with that? So molarity equals moles over liter. Moles is what I'm trying to find. So I do need to change my volume to liters. So 1,
Our
2,
initial
3.
or the N? Oh, N.
Yeah, because that's the amount of base that we added. So I added this much base. Okay, solve for X. So I'm going to times this over. Keep in mind, 0.1 just means you move the decimal again. So X is going to equal 0.00259. So this is how many moles of base I have, which equals
Which is equal
The
to
moles
this
of the
amount
acid.
of.
the moles of the acid, right? So this is the same thing as the moles of the acid. So now if I want the concentration of my acid,
We do that divided by 25.
good, so then divide it by how much acid we started with. Once again, make sure it's in liters. So 0.025 liters. Plug that in, and someone tell me what we get. Pretty much
0.1036.
0.1.
0.10.
36.
So 0.1.
Which for sig figs would round to 0.1. Okay, so, but that would be your answer. Questions on the math of the equivalence? That's really the bulk math portion. You don't really do much math here or here. It's more conceptual because like who cares about what the pH is in between? But understanding how to get to this is a big deal. So remember, step 1 was find the moles of base, and then we just take the moles of the base because it equals the moles of the acid and divide it by the volume. Okay, good. Okay, so if we keep going, What are we doing?
Just dump it in.
So what am I dumping in?
Make it blue.
So at my molecular view, what's
You're adding
More excess of the
Maybe blue before
NA.
purple.
and
Like,
no
hold
OH.
the blue for a second.
okay? So I'm gonna put that everything is the same
Plus OH.
plus more Na plus. Oh, I did this in the wrong color. But and OH minus, right? Because in a sense, there's nothing for it to react with, so it just continues onward. Now, Joel, can you answer your original question? Why does the pH have that drastic spike at the equivalence point?
Is it because all of the things, like since the pH is by powers and stuff?
Yeah, and as soon as you remove that last H plus,
It becomes.
jumps right up to 7, right?
Alright, here we go. So in theory, are we only gonna need one or no?
Well,
Say what?
Purple.
Oh yeah, I should have just, we could have kept going drop by drop and seen the point at which, right? But pretty much so. It's hard to get the blue because the blue's on the curve again, right?
Yeah.
But, so,
we should just get a universal indicator that's just blue. It's just blue feedback. That's it.
because you
Beautiful
just
shades
like the blue.
Like every shape, like
Why don't we
beautiful
get
shades.
something
I like green,
blue
blue colors.
maybe?
That's
Okay, any questions so far?
Look at my indicator, guys.
Okay, here's what we're gonna do now, okay? We're gonna walk through another titration. This time it's a weak acid with a strong base. We're gonna have a little bit more independence. So now what's gonna happen is before I draw it on the board, I'm gonna give you like 90 seconds per box. So we'll stop in between. And on your brain board, you're gonna draw me a picture of what you think should be in the box, and that's how you'll earn up to 20 smiley faces. Okay? Yep, so flip the page to the next one.
Ready?
So we're gonna do a second titration. A little bit different, but same concepts.
Another.
Does it fully dissociate even though it's a weak acid?
No.
Like, no, in the water though.
It's not water.
Or, okay, alright.
I'm not gonna answer it right now, but I'll answer it momentarily. Okay, so get your boogie board or your brain board.
Oh, I thought we were gonna put that up.
Well, I wanna make sure it's right before you put it in your notes.
Facts.
Okay, you got two, this one you probably don't even need 2 minutes for. Okay, so with your table buddy, draw me a picture. Here's our unknown weak acid.
Draw you a picture?
Okay, so you're gonna draw me a picture at the molecular level. What's going on inside this weak acid? Call it HA again. This ratio works better with 4. Do 4 molecules of acid.
4 molecules.
Okay, ready, set, go.
Wait, so it's a weak acid.
Weak acid.
What is in
I mean, I don't know how it probably be H, and then you have well, it's because it's hard to dissociate, so it's like, it doesn't, you'd still have some that's still, yeah, so it'd be like something that's something, because it's a weak acid. It's a ring about like 5%, but, I mean, that's not a proper percentage, but I'm guessing we're supposed to have that. Yeah, I think that. That's the only that's for both of them. They only dissociate and they are. I mean, there might be special cases that have that law, but I don't know about them.
She said there was
We're doing it again.
Why is the water like pink? Is it? Or am I just
Yeah, I don't think I rinsed it well enough, so it had some universal indicator already there, so it had a slight shade of it. Okay, everyone ready? 3, 2, 1, show me your brain.
Here's your brain.
Very small.
I think we were
But at least on the right track. What?
Okay, I think we're all there. Alright, so you can have one smiley face if you have
Yeah, what if we had?
No, I kind of talking about
You didn't have this happen, okay? But generally speaking, even a 3-to-1 ratio is like way big for a weak acid.
Oh,
Right? Keep in mind, like they dissociate like 5%.
oh, so.
But if you, yeah, you can still have one. Because it's hard with a small ratio. When you're only drawing 4, it's like,
Wait, what if we
you can have this. Don't ever do it.
Never.
Okay, everyone good? Everyone's looked good, so I'm assuming we're okay with our understanding there, right? So I poured my weak acid in here. Okay, right? Weak acids break apart to some extent, but most of them stay together as a combined unit, right? So that's why it is still less than 7, and our main equation at this point is our equilibrium. So write this equation in this box. So HA is breaking up into those two things. Right? pH is less than 7 because it is an acid, right? Now for this one, I'm going to add a different type of indicator just so you can see a difference. Because I know this situation, I'm picking an indicator that changes color at the pH of the equivalence point. So it's going to stay clear until we get to the equivalence point.
Ooh, so we'll never
So you
know what
won't-
color it is.
It's
yet.
slightly pink because I didn't clean my flask very well. But
So it's gonna
right
be-
now it's not going to change anything because it stays clear
So
at that
you're just gonna be magic.
magic. Yeah. Okay, questions so far? Okay. We're going to start dropping the base. Draw a picture on your brain board. What's happening as we drop the base?
Is it strong?
Yeah, NaOH.
But it's not. There'd still be some HA and we have one A minus. It made H2O not be like right away. So would it just would another one dissociate?
So that once it stays that color, we
It's not
retry.
just one. Like it's not
It just stays.
but like
So this is one of.
Wait, what base are we using? Oh!
So yeah, this is one of those that just does clear color. It doesn't have like three. So okay. Page of 8 is the flipping.
I think you'd have H2O.
Still,
Like you'd have
you want an NaOH.
like you're right. Yeah. I think so. Like just like and then
Okay, you got 15 seconds. Just put an X if you don't want me
close
to.
enough.
Tell me why.
All right, 10.
Would you give us a little, he's trying to explain it logically, so that way I can
Okay.
see if he's understanding.
Like would that
Sometimes it's like groups of the weekend. We talked about that in the lab.
well, because if it was still together.
Okay, show me your brains, please.
Oh, wait.
If it was together.
It's this one.
I know, some people need to draw bigger, like
Okay, I'll
it's a
do my
giant
better.
board for
I will do better.
I bought the 8.5 by 11 for a reason. Okay, keep them up, don't take them down. Don't take them down. You gotta put on your brain board.
Do you like our top hat guy?
We're matching with them too.
Okay,
He's a
ready?
spectator.
Don't erase it on your board so you can check and make sure as we go through the different points. Okay, so you can have 1 point, or not 1 point, 1 smiley face if you have created water.
No, he split water, not created it.
No, like, hit the rock.
Oh, I forgot about that.
Okay. Second thing, ready? This box has up to 5 smileys. There's a lot going on here. Okay, you can have a second smiley face if you still have HA together.
Yes.
Okay. All right, you can have a third smiley face if you have your spectator sodium in there. Good. You can have a fourth smiley face if you have some H plus and A minus, because some of the acid will break apart still because it's acidic. If you don't have H plus, what's the pH going to be?
Wait, why are there two?
It's gonna be sigma.
You have to have H plus if it's still acidic. Okay, and then the fifth smiley face.
If it's together, once it breaks up, that's when it's
The fifth smiley face is you should have just a leftover A minus.
We did it!
Okay. All right, write this equation down, ready? You should have HA plus OH minus. So this is the main reaction, is the OH minus is reacting with the HA. In that reaction process, we create the water and leftover A minus. That's why you have more A minuses than you do have H pluses, because the H plus is within the water now.
And it's a straight arrow because it's a
Because it fully reacts, right?
Oh.
Because we don't have any of this left over,
Okay.
right? So we have that, kind of like in the last activity, they talked about like if there's excess of things. So we do have excess HA, but we have no OH.
Okay. Okay.
Yeah, I did. Technically, it could be good. In terms of probability of ratios, it's most likely the HA, that's why we write the equation this way. But who knows to say it doesn't react with that? The catch is if we react with this, then it's going to break something else. But typically at this phase, that's why we always write it as HA's doing the reaction, not H. So yeah, great questions.
Well, the thing is, I don't know if there'd be like, I guess one of the things was like, at the equivalent when the moles are equal, that means like, yeah, the whole like is that
Generally, if they're both 1 molar, strong acid because the amount of, it's going to have more H plus, right? Okay, one more question and then we'll do our next box, okay?
So it's not gonna be as
Don't say it aloud.
this time.
Okay, think in your head. Just in your head this time. In this phase, this little whole section right here, okay, we are reacting a weak acid with a strong base. We've talked about something that gets created when you mix a weak acid and a strong base. What have I created? Write it down on your board.
Wait,
It's like a riddle.
I accidentally spaced out for 1 second.
So I'm mixing weak acid with strong base.
Am I allowed to look past at my notes?
What are you left over with?
I've created, there's something I've created. If I stop, I've made something. What could we call that thing I made? And it's not. Okay. 5.
I need to write it
4, 3, 2, 1. Take a guess. Show me your brains.
We're still processing. Is that a smiley face?
Oh, it's over.
So what I want to point out, everybody, that's significant here, okay? give me your eyes this way. Okay, you gotta look very detailed at the graph, but it's important. When it's a weak to strong, there's a big difference in this second region. Look at the graphics, okay? So this is weak to strong, look at that. This is strong to strong. What's the difference between the lines?
It's more consistent slope.
Yeah, everyone see that? Like, the strong one versus the weak one in the change that's happening. Because we've created this buffer thing that just gradually changes over time. Questions on that? So if you want to label it on your thing right here, this square is known as the buffer region. Now, there's a very important point within the buffer region that actually tells us information about our acid. And that is what is called the halfway to the equivalence point. So once you've done your whole titration and you have your whole graph out, if you go halfway from the equivalence point, so our equivalence point was like at, let's see if I can draw a line. I don't know, like right, is it right there on that line?
Yeah.
Okay, so that's the equivalence point. So that's 7, 8, 9, 10, 11. So if I go halfway from the equivalence point, so half of 11 is
6.5.
5.5, right?
Not 5.5.
You're good.
That's 6.5.
So this is the halfway point. If you match the halfway point up to your graph and take it over here, the pH at this point equals the pKa of your acid every time.
Wait,
So just the acid?
Yes, because that's the graph is primarily for the unknown. But if it was a reverse graph, it would be for the base.
Wait, is it 4.5 or 5.5?
5.5, because we titrated at 11, so half of 11 is 5.5.
Yeah.
So wait,
you drew it
So
at
that
4.
you threw it at 4.5. That's okay.
1, 2, 3, 4. I did the exact same thing.
Thank you. There we go.
So pH equals pKa.
So wait, so with the pH equals pKa, could you just cancel the p's on both sides and just like the H equals K?
I think so because of how logs work. You have to do the inverse of a log. Yeah, not that awesome.
What's the pKa again?
The pKa is the negative log of the Ka. And what's important here is that the Ka is the identity of the acid. So if you did not know, like you knew it was an acid, but it literally was HA to you, you could identify what acid it was by looking at its K, because there's K charts, right? Like we have one in our notes. And each K is unique for an acid. Okay. Questions on that? All right, we got to do our equivalence point. Okay, draw a picture. What's going on at the equivalence point? We got 2 minutes. Ready, go.
There's still gonna be some because we're getting rid of and then we have how would it be? Oh, at the yeah, okay, so we still have like one level. And then we have
Yes. It's the point at which the NaOH is the original acid.
good. I think I think there's still only one.
I think I killed it this time.
Got it? It gets a little crowded in this one.
We also split apart.
Based off of oh, stop scribbling on it.
Alright, you got 30 seconds.
You guys have your own? No, wait, actually say it.
That, like, well, those are The moles of the acid equal to the moles of the base that have an acid.
All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Show me your brain, please.
I'm a genius today. Am I locked?
It's alright, you might still get some even if you're wrong, right?
This would make the pH 7. But it's not 7. So how does that work?
Okay, let's go through it. Now I got a quick glance and check it as we go. Okay, first thing first, smiley face. Okay, so you can have one smiley face if you have drawn.
And not equivalence point, which is.
So we should have 4 water molecules that have been made. Because at the equivalence point, the moles of acid equal the moles of base. And if I started with 4 acids, then I should have
So there should be A minus.
I didn't know.
Okay. Ready for the next smiley? Okay, we got a hurt. Okay, the next one is you should have 4 Na pluses.
Oh shoot, I'm writing way too big.
Yeah, there's a lot going on in this
No,
box.
I didn't mean to circle it in that color.
Okay, and then the last thing is you should have 4 A minuses.
What if we have 3?
There's no.
Yeah.
Wait, do you mean?
But we didn't get any other smiley faces. So
Yeah, then you can. If you have A minus in your beaker, have a minus.
At least 1.
Okay, now, big takeaway before the bell rings. Someone mentioned, but wait, is the pH at 7 at this point? No, but it looks exactly the same as our other box did, right?
So how is it not?
So how is it not at 7? The difference is in the weak acid. What does a weak acid turn into?
Oh, H2O.
A base.
A weak
A minus.
base. Label this, everybody. A minus is a weak base. So what happens at the equivalence point is, yes, all of the original acid is gone. All of the base you dropped in is gone, but you create a base, right? You're gonna do a big box here. What do bases do when they react?
They turn into what?
Conjugate.
Faces.
Oh,
What's the behavior of a base? What do?
They take the H.
They take an
Yeah.
H plus. So this, I'm gonna do it up here. This A minus reacts with the water.
Oh, I can't. I don't know how to
It's
write.
fine, it's fine. And what would it make?
H
And
OH minus.
that's why it's bigger than 7.
Oh my god.
Is that the weak base that gets created creates some OH for you.
No way.
Does that make sense?
So how many smiley faces was that third box?
1, 2, 3, 4. What's significant is it's the moles of the original. The original acid equals the original base, but then you end up creating other base instead. So it's like the OH that's floating around is not from you dropping it in, it's getting Does that make sense? Your only homework tonight is just some titration stuff on AP classes. And finish the lab. And finish lab if you get some. Oh yes, and leave your smiley faces if you maybe want to. What were you doing?
Oh wait, is that like a color?
That's what I mean.
Yeah, one was rated down, then have an extra jacket.
I know, I gave up